So we showed in the case of a complex eigenvalue and a complex eigenvector that A ends up being what we called similar to this matrix C. And you say, great, what does that mean? A matrix is similar to another one. When you do the right basis switch, it's going to behave in a similar way to that matrix with respect to those vectors. If I take a matrix here, vector here, X, I'm going to switch basis. So I'm going to define a new basis. I'm going to call it gamma. And gamma is going to take the real part of V and the imaginary part of V. So we are going to switch this vector from standard language to this gamma basis. Now it's not an eigenvector basis because these are not eigenvectors. They are just parts of one single eigenvector. Then what am I going to do? I'm going to apply A. But in this particular case, when I'm in this basis, it ends up having the same effect as applying the similar matrix C. And then I'm going to change basis again back to the original. And then I'll end up with AX here. So it's kind of like going that way. What's the behavior of this matrix C? What does C do? All right, C is this matrix. A and B. Let's use polar coordinates again. And let's define that R. A squared plus B squared. If I wanted to, I could write this by factoring out an R and having A over R, negative B over R, B over R, A over R. And if I were to use polar coordinates again, I'd have an R, cos theta, sine theta, negative sine theta, and cos theta. This is a rotation by an angle theta counterclockwise. And then this is a stretch by a factor of R. And R is the magnitude, the size, the complex magnitude of the eigenvalue. So here is the point. In this gamma basis, which is the real part of the eigenvector and the imaginary part of the eigenvector, C just gives you a rotation and a stretch. The amount of rotation is just as we usually do when we talk about this polar interpretation, is just going to be the inverse tangent of the imaginary part over the real part. And that is now the whole point. This is why we ended up seeing the rotation and the stretching that we talked about before. If I give you some vector here in this gamma basis, and if I apply C, there's going to be a rotation by some angle theta. So I'll get it to there. If there was no stretch, I would end up there. And then there will be a stretch. So I will stretch by some factor there. R times this rotation times my original vector. So if I talked about the rotation matrix pi over 2, 0, negative 1, 1, and 0. The lambdas that we found were plus or minus I. So 0 minus I and 0 plus I. The one that we want to deal with is this one. Lambda is 0 minus one bunch of I. So in our case, A will be 0, B will be 1. Not negative 1, but 1. Because the point is, in order for us to use this machinery, we want this form A minus BI. When I have this eigenvector, lambda is negative I will find that its eigenvector is just going to be 1 and I. And if I wanted to, I could write this as 1, 0 plus I times 0, 1. So this would be the real part of the eigenvector. This would be the imaginary part of the eigenvector. So this matrix P is just the identity. The gamma basis is just the standard basis. the matrix C is A, negative B, B, A. Well, in our case, A is 0, B is 1, is just equal to R pi over 2. It's already the same thing. But here's the point of the story. If I were to take some vector, let's say 1, 0, and if I were to convert it to this gamma basis, it's already itself because it's standard basis. And that means that this vector x is going to be its own coordinate representation in this gamma basis. R will be the magnitude of my eigenvector. 0 squared plus 1 squared is just equal to 1. The amount of rotation is just going to be tan inverse. And then I will have negative 1 over 0. It's undefined. Or sorry, positive 1 over 0, undefined. So then what's going to happen is that it'll be a pi over 2. I'm going to take my vector that I start with, 1, 0, that's what x is. And if I were to apply the change of basis, I would be in this gamma basis. C is just a rotation by pi over 2. And there is no stretch because R is 1. So what ends up happening is that my image here, Rx in gamma basis, and if I were to switch back to standard basis, then I would find that Rx in gamma is exactly the same as Rx. So if I were to apply this in the context of a dynamical system, I would find that if I start with some vector here, x naught, it would just end up going by a 90-degree rotation every time I did this. So the trajectories would be circles in the phase plane. That's how the dynamical system would behave. If I were to take a larger radius, I would get larger circles. If I were to take a smaller radius, I would get smaller circles. These are called closed orbits, or sometimes they're called centers. Now, in the other example that we did, we had 0.5, we had negative 0.6, 0.75, 1.1. We found that the eigenvalue was 0.8 minus 0.6i. The eigenvector in this particular case was negative 2 minus 4i and 5. So that'd be negative 2, 5 plus I, negative 4 and 0. This is our gamma basis. The matrix that we are similar to is 0.8 minus 0.6, 0.6, and 0.8. And the reason is because this is A and B is 0.6. Remember, we want the eigenvalue with the negative there. So we're going to start with an x0. Let's say it's 2, 0. Now I'm hoping that because this is just a multiple of that basis vector, you will be able to see that the gamma representation of this vector would be 0 bunches of the first one. We'll call this V1, and we'll call that V2, and it'll be negative 1/2 bunch of the second vector. So in other words, x0 would be 0 V1s minus 1/2 of this V2. R would be 0.8 squared plus 0.6 squared, ends up being 1 again here. No stretch. And that's going to be curious. We'll have to talk about that. Theta is just going to be tan inverse of B over A, which is about 36.87 degrees counterclockwise rotation. Now we're going to evolve x naught according to this dynamical system. x1 in the normal basis would just be me, doing a straightforward matrix multiply with the vector in standard basis, and I would end up getting 1 and 1.5. Now, in gamma basis, the vector, the result in that gamma basis would be the same as just taking C and multiplying it by the gamma basis representation of this vector. 0.8, negative 0.6, 0.6, and 0.8, 0, negative 1/2. I'll end up getting a 0.3 and a negative 0.4. Our gamma basis was the set that contained these two vectors. It was negative 2, 5, negative 4, and 0. So that means the first eigenvector in my, or the second one here, this would be V2. So there's V2. And then V1 would live somewhere up here. Now, my original vector was x naught, and it was a half right there. So this is my x naught. It was basically a half of V2. Now, the result that I found right here, that x1 is 0.3, negative 0.4. So it's 0.3 bunches of V1 minus 0.4 bunches of V2. I don't know, a third of the way, so somewhere around there. And then it's got about negative 0.4 V2. So I'm pulling it in a little bit. So it's somewhere around there. If I were to do parallelogram rule with this right here, I would find that that's my result. That would be x1. x1 is 0.3 bunches of V1 minus 0.4 bunches of V2. And even from my crappy picture, you can see that in standard basis, this is 1 and 1.5, just like it's supposed to be. And this is what's happened. I have rotated the vector, and if I kept going here, it would go back. Now note, if I were to take this matrix 2, 5, negative 4, and 0, the determinant of this matrix isn't 1. And that means there's going to be a stretch when we change basis. And that's why it's not circles when we plot this behavior. It's ellipses. Yes, we're going to get this closed trajectory again, but because of the change of coordinates, these coordinates, V1 and V2, are what we call skewed. And as soon as we have a skewed set of basis vectors, we're going to get these distortions. They won't end up being circles. They'll end up being ellipses. If we have a dynamical system and we ever get these complex eigenvalues, we know that if the size of the eigenvalue is 1, we'll end up getting these closed trajectories. If I were to ever have eigenvalues that were less than 1, so for every application of the matrix A, we would get a shrink. We'd get this cumulative r to the power of k factor. Every time I would apply it, so if I were to start there, I'd have a rotation, but I would be sucked in. And so what you would find is that eventually, no matter where you start, every trajectory would take you back to the origin. So that means this origin would be what we call a spiral attractor. Now, at the same time, if our eigenvalue was greater than 1 in size, we would grow for every application of A. We'd have this r to the k factor that would just grow and get big. And so when we were to plot trajectories, everything would emanate from the origin and rotate and grow in size. There would always be a rotation, and there would always be a growth in the size. So 0 here would be a spiral repeller. Everything would be pushed out.